Welcome everyone. Today, we are going to delve into two critical mechanisms in Hadoop Distributed File System, or HDFS, heartbeats and block reports. These are fundamental to the health, consistency, and fault tolerance of HDFS. We'll explore how they work, how they are configured, and their role in maintaining a robust distributed storage system. Before we get into the specifics of heartbeats and block reports, let's set the stage with an overview of HDFS communication. HDFS is a distributed storage system designed for fault tolerance and scalability. It follows a master-slave architecture. The master is the NameNode, which manages the file system metadata, including the mappings of files to blocks and the locations of these blocks across the cluster. The slaves are the DataNodes, which store the actual data blocks. To ensure the cluster remains healthy and data remains consistent, HDFS relies on two key mechanisms: heartbeats and block reports. Heartbeats are periodic signals sent by DataNodes to the NameNode to indicate they are alive. Block reports are messages that inform the NameNode about the blocks stored on each DataNode. Together, they form the backbone of HDFS's self-healing and consistency capabilities. So, what exactly is the purpose of heartbeats? First and foremost, they are the lifeline between the DataNodes and the NameNode. They serve two primary functions: confirming the liveness of a DataNode and reporting the resource availability on that DataNode. By liveness, we mean that the DataNode is up and running. Resource availability includes information such as storage capacity and current workload. These heartbeats also trigger critical actions by the NameNode. For example, if a DataNode fails to send a heartbeat, the NameNode may initiate re-replication of blocks that were stored on that node to maintain the replication factor. Similarly, if the NameNode detects a DataNode is alive but overloaded, it might adjust block placements. In essence, heartbeats are the pulse that the NameNode uses to monitor the health of the cluster. Now, let's look at how heartbeats work mechanically. By default, every DataNode sends a heartbeat to the NameNode every 3 seconds. This interval is configurable. Each heartbeat message includes several pieces of information: the DataNode's unique identifier, its current storage usage, how much disk space is used and available, and its current workload, like the number of ongoing transfers. This information allows the NameNode to have an up-to-date view of the cluster's state. The heartbeat is sent via an RPC remote procedure called to the NameNode. It's a lightweight message, so sending it every few seconds doesn't impose a significant overhead but provides near real-time monitoring. One of the most critical aspects of heartbeats is failure detection. The NameNode uses the absence of heartbeats to determine if a DataNode is dead. How long does it wait? The default timeout is 10.5 minutes. This is calculated as 10 minutes and 30 seconds, which is derived from two configuration parameters: the heartbeat interval 3 seconds and the heartbeat recheck interval 5 minutes. Specifically, the formula is 2 * dfs NameNode heartbeat recheck interval plus 10 * dfs heartbeat interval. When a DataNode is marked as dead, the NameNode triggers re-replication of all the blocks that were stored on that node. This ensures that the replication factor for each block is maintained, thus preserving data durability and availability. Let's talk about configuration. The heartbeat interval is controlled by the parameter dfs heartbeat interval, which is set to 3 seconds by default. This defines how often a DataNode sends a heartbeat. The other important parameter is dfs NameNode heartbeat recheck interval, set to 300,000 milliseconds or 5 minutes. This parameter defines how often the NameNode checks for the receipt of heartbeats. Together, these two parameters determine the failure detection timeout. It's important to note that changing these values can impact the cluster's responsiveness to failures in the load and the NameNode. For example, a shorter heartbeat interval might detect failures faster but could increase network traffic and NameNode load. Now, let's turn to block reports. While heartbeats are about liveness, block reports are about data integrity. The primary purpose of a block report is to inform the NameNode about the blocks stored on a DataNode. This includes the block IDs, their lengths, and their generation stamps. Block reports are crucial for the NameNode to maintain accurate metadata. They also help in detecting mismatches such as corrupt blocks or missing blocks. For instance, if a block is reported as corrupt by a DataNode, the NameNode can schedule the replication of a healthy copy to another node. Similarly, if a block is missing, i.e., it's in the metadata but not reported by any DataNode, the NameNode can trigger re-replication from an existing replica if available. Block reports come in two flavors: full block reports FBR and incremental block reports IBR. A full block report is sent by a DataNode every 6 hours or immediately upon startup. This report includes the complete list of blocks stored on that data node. On the other hand, incremental block reports are sent whenever there is a change in the set of blocks on the data node. Specifically, IBR are sent along with heartbeats if there have been any block additions, deletions, or modifications since the last report. This incremental approach reduces the load in the NameNode because it only processes the changes rather than the entire block list. Here's the step-by-step process flow for block reports. First, the DataNode periodically scans its local storage. For an FBR, it compiles a complete list of blocks and their metadata. For an IBR, it compiles only the changes since the last report. Then, the DataNode sends this report to the NameNode via RPC. The NameNode receives the report and reconciles it with its own metadata. This reconciliation involves updating the block map, removing blocks that are reported as deleted, and adding new blocks. If any discrepancies are found, such as a block that is supposed to be on this data node but isn't reported, the NameNode can take corrective actions. Configuring block reports involves two main parameters. The first is dfs.blockreport.intervalMsec, which sets the interval for full block reports. The default is 21,600,000 milliseconds, which is 6 hours. The second parameter is DFS DataNode directory scan interval, set to 21,600 seconds, also 6 hours. This parameter defines how often a DataNode scans its local directories to detect any changes to the blocks. It's important to note that even if the directory scan interval is set, the IBR are sent immediately when changes occur, so the scan interval primarily affects how quickly the DataNode becomes aware of changes made outside of HDFS, like direct file manipulations. Now let's discuss how heartbeats and block reports interact. Incremental block reports are sent along with heartbeats whenever there are block changes. This means that if a DataNode has added, deleted, or modified blocks, it will include an IBR in its next heartbeat. In response to a heartbeat which may contain an IBR, the NameNode can issue commands to the DataNode. These commands might include instructions to replicate certain blocks to other nodes, delete blocks that are no longer needed, or recover leases for files that are being written. This two-way communication ensures that the NameNode can actively manage the cluster based on the latest state. Let's consider some failure scenarios. If a DataNode stops sending heartbeats, the NameNode will eventually mark it as dead after the timeout period 10.5 minutes by default. This triggers block re-replication from the remaining replicas. However, network partitions can cause false positives. A DataNode might be alive but unable to communicate with the NameNode. In such cases, when the partition heals, the DataNode will rejoin and send a full block report. The NameNode will then reconcile and may cancel any ongoing re-replication if the blocks are still intact. Another scenario is corrupt blocks, which are detected via checksum verification. When a DataNode reads a block and finds a checksum mismatch, it reports the block is corrupt to the NameNode, which then schedules replication from a healthy replica. In more advanced deployments, there are additional considerations. For instance, heartbeats can include storage tier information, such as whether blocks are stored on SSD or HDDs. This allows the NameNode to make tier-aware placement and replication decisions. Also, in a high availability setup with active and standby NameNodes, DataNodes send heartbeats to both NameNodes. This ensures that the standby NameNode is also kept up to date. Additionally, to handle a large number of DataNodes, you might need to tune the parameter dfs NameNode handler count, which sets the number of threads in the NameNode to process RPC requests. Increasing this value can improve scalability but also consumes more resources. Monitoring is key to maintaining a healthy HDFS cluster. You should regularly check the NameNode and DataNode logs for any warnings or errors related to heartbeats or block reports. Hadoop also provides JMX metrics that you can monitor, such as heartbeats received, the number of heartbeats the NameNode has received, and pending replication blocks waiting to be replicated. Additionally, there are command line tools. HDFS admin report gives a summary of the cluster status, including live and dead nodes, and HDFS FSEK/files blocks checks the health of the file system by verifying blocks and their replicas. These tools are invaluable for troubleshooting issues like missing blocks or under-replicated blocks. Here are some best practices. First, tune the heartbeat and block report intervals based on your cluster size and network stability. Shorter heartbeat intervals allow faster failure detection, but increase load. Second, ensure that your network is reliable and has enough bandwidth to handle the heartbeat and block report traffic. Third, monitor disk capacity on DataNodes to avoid running out of space, which can cause blocks to be under-replicated. Fourth, validate your configuration by testing failure scenarios. For example, you can manually decommission a node or simulate a network partition to see how the cluster responds. This helps ensure that your recovery mechanisms work as expected. In conclusion, heartbeats and block reports are the twin pillars of HDFS's reliability. Heartbeats ensure that the NameNode is aware of the liveness and resource status of each data node, enabling quick detection of failures and triggering recovery actions. Block reports ensure the metadata accuracy by informing the NameNode about the block stored on each data node, allowing it to maintain data durability and consistency. Together, they enable HDFS to self-heal and maintain a consistent state across the cluster. Understanding and properly configuring these mechanisms is essential for any HDFS administrator. Thank you.